I think my mind is just about to be blown. So what I'm trying to do here is a second take on the Bernstein algorithm, and I was trying to figure out what's going on, like why we have all these Hadamards, and those are those entanglements, are those not entanglements, and actually that's been super helpful to play with that. So let me just walk you back through the way that I'm going to keep the measurements, right? But I'm going to remove this. So I'm basically just trying to recreate the circuit, and I was like trying to stand, with by taking a look at the state vector on that side of the screen, see what happened, right? So that's our starting point. So and then when we have identity here, just so it's clear, those operations make nothing, but at least it's clear. It's sort of it's sort of one to what we see in in here, right? Especially because here I have to prepare that qubit to be one, so I have to apply a next gate. So so when I'm applying here the Hadamards, right? So what we basically end up with is because of the one here, right? We end up with basically two clusters of possible states, and you see this because of the color. And the reason is because when you apply Hadamard on one, you end up with the phase the sort of a minus, right? So the phase would be negative, in which like the probabilities are not affected. If I take a look at the measurement probabilities, it's just equal probabilities, but you can see that there is a minus in those coefficients here, right? And that's because we've applied a Hadamard on a qubit that's one, that's not zero. And so now what we're gonna do is we're gonna create an entanglement, but not within the same dimension, right? But entanglement between those two clusters. So when I do this, right, I'm basically shifting that. I'm not so sure if you can kind of see the entanglement here or not, but I'm basically, so what's happening is we're shifting where the phase is, and I have to edit that. This needs to be here, right? Good. So now what we have, if you see what's happened here with the colors, is that the two clusters now are separated by what? By basically so got 0 1 1 0 0 0 1 1. What is the difference of the clusters now here? So 1 1 1 1. So basically, okay, so and that's the entanglement, right? So basically look at this. So what you've done is that that the pairs where the qubit 0 and qubit 1 always agree, like are the same 0 0, so this one here and this one here, they are then in different clusters, right? 0 1 and 0 1, 1 0 1 0 1 1 1 1. Does this make sense? I think that's what's really happening here, because now what we'll see is as I add the next Hadamards, that we're gonna start losing some of those states. So now we've lost everything that has a 0 as a possible value for the qubit 0. And this is because that entanglement that we've created here, right? Let me check. So this and this. Yeah, because basically they just cancel each other. That's what's happening, right? Because you've got the two different clusters. I think that's what's happening. Bam. When I now do that, I'm losing. When I now do that, I'm losing the ones where this is supposed to be 0. Exactly. Because when I do that, then I'm done, right? So then we end up with that. The question is why. So I think this has to do with the fact that there is a 1 here. Because if we didn't have a 1 and we had an identity here, then we would end up with the state 0, 0, 0. So you're recovering that 0, 0, 0. So, but essentially that is there's something happening here with the entanglement between those, because let's go back to this. So we've got here two clusters, right? And the way this is clustered now is, because if I were to now just do again Hadamarts, right, I would end up with just 1, 0, 0, which is what I had here. But why? Because they cancel each other. But now the trick is, what am I doing with this? Is when I do something like that, what's the change? Is that I'm moving those minuses, right? So the colors are moved, and now the colors are, what is the cluster now? So now the clusters is everywhere where, okay, so it's everywhere. I see, because so originally those two things disagree, right? Because it's a 0 and a 1. So now basically the cluster is, because I've done this, so the way this is entangled now is that for all the pairs where the qubit 2 and 1 disagree, then we've got a minus. So we have got the yellow color. That's what we have done, right? So, and if I now add another one, but not this way, but this way, what we're saying is now do the same for the qubit 2 and 1. So basically what this is doing is, for all the so it's sort of entangled all the states where it's flagged. Okay, it's flagged all the states where there is an it's flagged all the states where there's an uneven number of ones. Right, because it's either 0, 1 or 0, 1 or 1, 0, or just like it's an OR, so it's like 1, 1, 1, 1, right? Exactly. And so as I add Hadamarts now to go back to where we were, then there's sort of some canceling out that's happening here. So if I do that, we're gonna lose all of those where we had a 0. I still don't know exactly why this is being cancelled out. I guess is because there are 0, 0, 0, 0, 0, 0, they get cancelled because this, and then mm, this gets cancelled. Yeah, with this, I think that's kind of what's happening. So they getting cancelled, right? Um, and now we've got left those where this one and sorry, this where we've got zeros, and these will get cancelled. Exactly. And now here is the final trick. Here is how we end up just with this one as a final probability. Is simply based on the fact that it's based on the fact yeah, so in this case, when we have a Hadamard, we can only keep one of those states. So that's because we're kind of moving the certainty again into our measurement basis, right? Because we've gone into uncertainty, so we've gone into like a superposition, and now we're going back. That's what we're essentially doing. But because we've got them flagged, right? The one that we're losing is the one that so the one that we're keeping is the one that's flagged. That's for sure. I'm not so sure exactly where why this is this way, because if I would now say that is not an X but like an identity, so yeah, but now end up with totally different possibilities, and now nothing's flagged. So the fun part is when this is an X, because then things get flagged, right? So because what we would do if we wanted to implement that, not for the secret being 1 1, but for the secret being 0 0, my assumption is I just add XX here, right? And then uh, and then that's it. Then you got it, right? Because then when you do that, you end up with 0 0, right? So the trick here is it has to do with this one being entangled. That's what allows for the cancellation. Kind of for the cancellation of states to happen. Mm-hmm. But it's interesting to see that that's the type of entanglement you're doing, right? So you're entangling um, between two dimensions. So you're entangling with the sign, so to say, with a minus sign, with a phase. And then by going back into the dimension where you've got the certainty, or bringing back the certainty onto the measurement, onto the z dimension, you're along the way losing the information you don't want to. You're virtually losing it, right? It's still there, but you're losing it, and so when you measure, you're going to get what you want. So pretty cool. But I'm trying to still figure out what's the effect on and why. So the reason this is a 1, it's important because that's what's allowing for that type of entanglement, Exactly. That's what's allowing for the type of entanglement. And at the end of the day, it's the same you're doing with the Dodge algorithm, just with 2 qubits. But that's what's allowing for this type of entanglement. Um, mhm, mhm. And I guess there's different ways to look at it, but that's really it. Uh, so and, mm, mm, mm. Why though we're getting that value? That's what we want to have. Mm, well, because we're recovering originally what we had here, right? Yeah, but then those are not. It's that's definitely interesting. I think I'm gonna even make another video on that. But that's an awesome tool to explore that. I think that we're onto something here. Cool.